In this video, we're going to talk about a strategy for finding all of the complex nth roots of a given complex number. So let's start with a problem. So here's a question. What are the square roots of 64? So remember, to be a square root of 64 means that you are a number whose square is equal to 64. And we can think of two of those. There's what we call the principal square root of 64, which is 8. And then there's also the opposite of that, which is negative 8. Each of those is considered to be a square root of 64 because each of those numbers squared is 64. We do consider the principal square root to be the non-negative square root of the number, and that's a convention that we use when talking about functions. But for algebra, we want to be able to think about all of the square roots. Those include 8 and negative 8. And from an algebraic point of view, it makes sense for there to be two square roots, because when we talk about square roots of 64, what we're really doing is something equivalent to solving the equation x squared equals 64, or if you like, x squared minus 64 equals 0. In other words, we're finding the roots of, or zeros of, the polynomial x squared minus 64. And one thing we're going to learn is that it makes sense algebraically for this polynomial to have up to two roots. All right, now let's talk about cube roots. So here's another question. What are the cube roots of 64? So equivalently, we might ask, what are the roots or zeros of the polynomial x cubed minus 64? If we're thinking entirely in terms of real numbers, we know of one answer to this question. One of the cube roots is 4, because we know that 4 cubed is 64. And you might think, well, what about plus and minus 4? But if we take minus 4 cubed, we end up with negative 64, not positive 64, so that does not qualify as a cube root. So negative 4 is out. So we have one cube root, but it would be kind of algebraically elegant if we had 3 of them, because this is a polynomial of degree 3. It would be lovely if it had 3 roots. It's not mandatory that a polynomial of degree 3 has 3 roots, so that's not necessary. It's just it'd be nice if it did. But it turns out in the complex numbers, that polynomial does have exactly 3 roots. And in this video, we're going to talk about how we find those. So that's the background for what we're doing here. So now let's talk about how we find those. In a previous video, we talked about the fact that, and this is called de Moivre's theorem, we talked about the fact that if you have a complex number expressed in polar form, z equals r cis theta. And just as a reminder, r is the magnitude of the complex number. That's the square root of a squared plus b squared, where z is a plus bi. And then theta is the argument of the complex number. Let's write that down. So this is the argument. And I'm not going to write down a formula for it, but I'll just say it's the angle measure from the positive real axis measured counterclockwise. If we have those two pieces of information, then taking powers of z is not too hard, as long as we use the geometry of complex numbers. So de Moivre's theorem is that z to the n, for n any integer, this is assuming the magnitude is non-zero, z to the n is equal to r to the n times cis of n theta, which can be expressed in longhand as r to the n times cosine of n theta plus I sine n theta. In other words, the nth power is a complex number whose magnitude is r to the nth power of the original magnitude, and whose argument is n times the original angle measure. And that's how we take powers of complex numbers. And once you know how to take powers, figuring out how to take roots is just a matter of figuring out how to reverse that process. So for an example, let's look back at the question that we were just trying to answer. What are the cube roots of 64? We know that there is one real cube root. And in fact, there is only one real cube root, because as a function of x, a real variable, this polynomial function, x cubed minus 64, is increasing. It'll only cross the x-axis one time. So if we want to find additional cube roots, we're going to have to look to the complex number system, where we will in fact find two more of them. All right, so let's ask ourselves the question, what complex numbers have cube 64? In other words, what complex numbers are cube roots of 64? Well, as a complex number, 64, if I think about the complex plane, 64 is over here on the positive real axis. So it can be expressed as a complex number whose magnitude is 64 and whose argument is 0. So now if I'm thinking of some complex cube root z, if z cubed is equal to 64, then z has to be expressible in the form r cis theta, such that r cubed cis of 3 theta is equal to 64 cis of 0. Now let's think about that. We know that we want the magnitude r cubed to equal 64, and magnitude has to be a non-negative real number, so r is going to have to be 4. So what we found out originally when we were looking for cube roots is something that has to be true of all complex cube roots. The magnitude has to be 4, just like it was for the real cube roots. So r has to equal 4. But then what about theta? We need 3 times theta to equal 0. So we get theta equals 0. So z is equal to 4 cis of 0, which is equal to 4 cosine 0 plus I sine 0. Cosine of 0 is 1, sine of 0 is 0, so we end up with 4. Wait a minute. That just gives us the complex cube root we had earlier, which is 4. By the way, if a number is real, it still counts as a complex number. The word complex is not a synonym for not real. Real numbers are included among the complex numbers. But the real concern here is that I just promised you we were going to find 2 other cube roots, and we only found the one that we already had, which is 4. Okay, so in order to find the other ones, we have to think a little bit more creatively about that theta. Because I wrote down something here that actually doesn't have to be true. That theta ends up having to equal 0, which was based on 3 theta having to equal 0. All right, so it is true that 3 theta needs to be in the same position in the complex plane as 0. But that doesn't imply that theta has to be 0. There are other thetas between 0 and 2 pi, such that if I triple that angle measure, I get back onto the positive real axis. So what thetas are those going to be? Well, to find them, one way we can approach this is we can say, what if 3 theta were not equal to 0, but were equal to 2 pi, which would be in the same position as 0. Well, then theta would be equal to 2 pi over 3. And then we would have z equals 4 cis of theta, which is 2 pi over 3. So that'd be 4 cosine of 2 pi over 3 plus I sine 2 pi over 3. And that would give us, geez, what is cosine of 2 pi over 3? Cosine of 2 pi over 3, the angle 2 pi over 3 is up this way. It's at a 120 degree angle from the positive real axis. So that cosine is going to be negative 1/2. 4 times negative 1/2, and then the sine is going to be root 3 over 2. So I end up with negative 2 plus 2 root 3 I. And that, I claim, is one of the other complex cube roots of 64. Don't take my word for it. Try multiplying it out. You only have to multiply 3 times. You can do it. If you multiply that by itself 3 times, you actually will get 64. It's crazy but true. Okay, but that's only one other complex cube root. We still are looking for another. But let's see here. So if having 3 theta equal to 0 would work, and having 3 theta equal to 2 pi would work, then what about 4 pi? What if 3 theta had been equal to 4 pi? What would that give us? Well, then theta is going to be equal to 4 pi over 3, which in the complex plane is this direction here. Notice that that's the reflection of this other direction across the real axis. That's not a coincidence. We'll see more about that later. But anyway, if theta is 4 pi over 3, then we get z equals 4 cis of 4 pi over 3, 4 pi over 3. And that gives us 4 cosine of 4 pi over 3 plus I sine 4 pi over 3. And after calculating, you're going to get negative 2 minus 2 root 3i. Notice that's the conjugate of the one that we got earlier. Again, not a coincidence. More about that later. So now we have 3 complex cube roots. But you might think, well, wait a minute, why do we have to stop there? What if we were to take 3 theta equal to 6 pi? So let's ask that question. What if 3 theta were equal to 6 pi? Then we would get theta equals 2 pi, and then my complex number would be, my cube root would be z equals 4 cis of 2 pi, and then I realize, oh, if my position is 2 pi, that's along the positive real axis. I'm probably going to get exactly the same thing I had before. So 4 cosine of 2 pi plus I sine of 2 pi, and again, cosine of 2 pi is 1, sine of 2 pi is 0, so now we're back on 4, which is a cube root that we already had. So at this point, taking additional multiples of 2 pi doesn't reveal anything new. We just have the 3 complex cube roots, 4, which we found the first time, negative 2 plus 2 root 3i, and negative 2 minus 2 root 3i. There are 3 of them, and you'll notice that they are equally spaced around the origin in the complex plane. In other words, I can graph those, and this is going to be slightly not to scale because drawing 1/16 of this distance here is going to be indiscernible from the origin, but I'm going to get one here at 4 units away from the origin, that's at 4, and then one here along this ray, and then one here along this ray, and those actually form an equilateral triangle. It's very pretty. Okay, in general, and this is a generalization of what we just did. In general, complex nth roots of a number, any complex number, and here we started with 64, which was real, but you could start with any complex number. And the complex nth roots of w, a complex number, provided that the complex number is non-zero, the nth roots are going to have the following properties. First of all, they're all the same magnitude. All the same magnitude, and that magnitude is the nth root of the magnitude of the original w. Okay, so whatever w's magnitude is, the magnitudes of the nth roots are going to be the nth root of that. And they're going to be equally spaced around a circle of that radius. So they're equally spaced around a circle of that radius centered at the origin, and consecutive roots are going to be 2 pi over n radians apart. And the reason for that is just see what happens when you run this strategy that we did for cube roots of 64 on a general complex number and trying to find nth roots. Okay, you're going to be taking additional multiples of 2 pi when interpreting the argument of this number, and you're going to divide those multiples of 2 pi by n, hence the 2 pi over n radians apart. So this gives us a general strategy for finding complex nth roots of a given complex number. What this means is that you can answer questions that maybe you wouldn't have been able to answer so efficiently before. For example, what are the square roots of the complex square roots of I? You know that I is equal to the square root of -1, but maybe you've never thought about what are the complex square roots of I. Is there even such a thing? Well, now you can actually find that there are square roots of I. There are 2 of them in the complex plane, and you can even figure out what they are using this strategy of writing I in complex polar form and then using the polar form to figure out what the square roots would be. So anyway, that is a brief crash course in finding complex nth roots of a complex number. We'll use that later in the course to analyze roots of polynomials.